Okay, in this video we're going to learn about the concavity of a graph, what it means for a graph to be concave up or concave down, and how to determine points at which the graph of function changes concavity from concave up to concave down or vice versa. These points are called inflection points, or in certain contexts it can be called a point of diminishing return. So first I'm going to show you a couple of graphs. Here I have a graph of a function that has several inflection points. So when the graph is facing downward like this, versus here where it has happens to have a maximum, here the graph is concave down. But over here, the graph is opening upward, the graph is concave up. So the point at which the graph changes this kind of concavity from concave down to concave up, right here, is an example of an inflection point. So from this point forward, the graph is concave up, but then at some point, around, by the time we get to here, it changes concavity again. Now it's opening downward again, it's concave down. So again, the point where it changes from concave up to concave down, that also is an inflection point. And then we have one more over here, because here's concave down, but now it's concave up again. Wherever change happens, also an inflection point. So this graph has a total of three inflection points. To determine conclusively from a graph whether it's concave up or concave down at a certain point, what you can do is always draw a tangent line. And I'm going to do that in a couple of cases here. Here, the graph is concave down. So I'll just mark a particular point here and draw the tangent line. And here we see that the graph of a function is below the tangent line at that particular point. Whereas if I pick a different point, like this one right here, and draw the tangent line. Here, the graph is above the tangent line. So when the graph is above its tangent line, it's concave up. When the graph is below its tangent line, it's concave down. So you can always use that to visually determine concavity. So one of the problems in Hawks, you're given only a graph of a function, not a formula, and certain points in the graph are marked, and you need to determine if those points are inflection points, and then give the x-coordinates. Here's another example of an inflection point. Here the graph is changing from concave up to concave down. So in certain business applications, this inflection point, which is the same kind of point as these other inflection points from the previous example, is referred to as a point of diminishing returns. So for example, if x refers to the number of units sold, and then y refers to the total revenue. Certainly the revenue is going to be increasing the more units you sell, but at some point you're not going to gain as much revenue. So that's why we say point of diminishing returns. So here the rate of change of revenue with respect to units sold is increasing sharply, but then the increase is not as much. So the inflection point is therefore referred to as a point of diminishing returns in this setting. Now, and I bring that up because one of the Hawks problems refers to identifying the point of diminishing returns. So the problem calls for finding an inflection point. So now in this example, you have a formula for a function, and I'm going to show you how to find the inflection points, and also determine intervals on which the function is concave up or concave down. Now this is somewhat similar to problems you've done in the previous lessons, where you had to find the intervals in which a function was either increasing or decreasing. The difference is, when you're finding where a function is increasing or decreasing, you're determining where the first derivative is positive or negative. For finding intervals where a function is concave up or concave down, you're trying to determine where the second derivative is positive or negative. So be sure to keep straight which derivative you need to deal with for determining increasing or decreasing, or concave up, concave down. So here we're going to determine concave up versus concave down. So, and for that we need the second derivative. Well, to get the second derivative, you need to compute the derivative, which we now refer to as the first derivative. So carrying out differentiation once gives us the first derivative. Carrying out again on the result gives us the second derivative. So before I carry out differentiation, I'm going to rewrite this function in a form it's more suitable for differentiation rules using a fractional exponent. So 7x squared plus 21, the whole quantity, raised to the 1/3 power. So now I can differentiate that using the general power rule. Okay, so what we get from differentiating using a general power rule is 1/3, 7x squared plus 21, raised to the 1/3 minus 1, which is minus 2/3. And that times the derivative of what's inside here, which is the derivative of 7x squared, but plus 21 is not going to contribute anything. The derivative is about 0. So we just get 14x. Okay, that's the first derivative. But now we need to take a derivative of that to get the second derivative. I can give myself a little more room here. So I have I'm going to have a 1/3 multiplying everything. So I'll just put everything else within these square brackets. So but this is a product, so now I have to use the product rule. So I have 14x times the derivative of 7x squared plus 21 to the minus 2/3. That plays out pretty much like before. Minus 2/3 7x squared plus 21 to the minus 2/3 minus 1, but that's minus 5/3 times the derivative of what's inside here, which again gives me 14x. And then, to complete the product rule, I now have 7x squared plus 21 raised to the minus 2/3 times the derivative of 14x, but that's just 14. Okay. So now the second derivative is complete. It's a bit of a mess. So now we need to determine where this derivative, the second derivative, is equal to 0. So one thing that will help is if I can factor out as much as possible. So I have a 14 in each term, so I can factor that out. But besides that, these expressions, 7x squared plus 21 to the minus 5/3 and minus 2/3, those can make it difficult to determine where this whole expression is equal to 0. But if I factor out judiciously, I can actually make the process a whole lot easier. But that's what makes this problem a little tricky. So this is a good technique for you to know. It can be useful in other problems where you have to use the product or the quotient rule for that matter. So in order to get rid of any expressions inside here that would involve radicals, I'm going to factor out 7x squared plus 21 to the minus 5/3. Now, it may seem difficult to fathom how I would go about doing that, but think of it this way. If I put, well, first I still have a 1/3, and I'm also going to factor out a 14. I have a 14 here and a 14 here. So I'll factor that out as well. And so now what happens is if I factor out a 7x squared plus 21 to the minus 5/3, then to compensate for that, so basically I'm just putting a 7x squared plus 21 to the minus 5/3 here. Then in order to compensate for that and make sure that the whole expression doesn't change, I need to multiply throughout by 7x squared plus 21 to the plus 5/3. Now that may seem like madness, but you'll see that it actually makes things easier later on. So I've already factored out a 14 here, so I'll just have an x. And then I also have this 14x over here. And then I also have a minus 2/3. And so now if I take 7x squared plus 21 to the minus 5/3 that's sitting here, and multiply it by 7x squared plus 21 to the plus 5/3 to compensate for what I wrote here, then they will cancel each other out. So that's it. I won't have anything else for my first term. So I just have the x, 14x, so minus 2/3, And that's it. I already factored out 14. Now, over to the next term, this term of this factor of 14, that also has been factored out, so I can forget about that. And now I have 7x squared plus 21 to the minus 2. Recording interrupted again. Okay, to the minus 2/3 times 7x squared plus 21 to the positive 5/3 to compensate for 7x squared plus 21 to the minus 5/3 that I wrote out here earlier. So now I have the same base with different exponents multiplied together. So what I would do is, because they're the same base, I add the exponents. Well, minus 2/3 plus 5/3 is equal to 1. So now what I have is, I have all this out here, 7x squared plus 21 to the minus 5/3. And now I'm going to simplify this as much as I can. I have minus 28x squared over 3. So just from multiplying all these together and simplifying, plus 7x squared plus 21. So now the second derivative is simplified as much as possible, and I now need to find out where it's equal to 0 to determine the inflection points. Now, second derivative is equal to 0 if and only if either this is 0 or if this part is 0. But this part can never be 0. 7x squared plus 21 is always going to be strictly positive. So I can ignore this part and just focus on this. So one thing I will do to simplify things more, I'm going to factor a 7 out of all this. So now I have 7/3 14 7x squared plus 21 to the minus 5/3. And now factoring 7 out of everything here, because everything here, the numerator is divisible by 7. So I have minus 4x squared over 3 plus x squared plus 3. So now I'm going to simplify this, because I have x squared minus 4/3 x squared. So this simplifies to minus x squared over 3 plus 3. So now I'm going to set this equal to 0. So minus x squared over 3 plus 3 is equal to 0. So I'm going to move a first term to the other side. So I have 3 is equal to x squared over 3. So I can multiply both sides by 3. 9 is equal to x squared. So x is equal to plus or minus 3. So at these points, the second derivative is equal to 0. Now, to determine, these are candidates for inflection points. To determine if they actually are inflection points, what I need to do is substitute other x values into the second derivative to see if what I get is positive or negative. So it's like when you did a sign chart for the first derivative to determine increasing or decreasing. You found out where the first derivative is 0, your critical points, and then you looked at points in between the critical points to see if the first derivative is positive or negative. If it was positive, it was increasing, negative, it was decreasing. This is similar. I'm going to draw a sign diagram. So that means I draw a real number line, and I'll mark minus 3 and 3 on the real number line. And I will check points in, so here, f double prime equals 0, and here 2. So I will check points in other than minus 3 or 3, so 1 point in each of these 3 regions to determine whether the second derivative is positive or negative. If it's positive, it's concave up. If it's negative, it's concave down. Okay, so now I need to return to the simplest form of the second derivative that I have. But to determine if it's positive or negative, I don't have to evaluate this whole expression. This part, as I mentioned earlier, is always positive. So whether the second derivative as a whole is positive or negative is determined entirely by whether this part right here, that I've simplified as much as possible, whether this is positive or negative. So for example, suppose I I choose x equals 0, because that is in between my two possible inflection points. So I plug in x equals 0, and I get 3, so the second derivative is positive. Okay. And then, if I could choose, for instance, a point over here, like x equal to minus 4, let's say. So I substitute in x equal minus 4, so I get minus 16 thirds plus 3, but that's going to be negative. So I have a double prime is negative out here. And similarly, if I substitute x equal to, let's say, positive 4, any point out here that's greater than 3, I'll choose x equal 4, so I get minus 16 thirds plus 3 again, and that's going to be negative. So we can conclude that the function is concave up on the interval minus 3 to 3, and concave down on the interval, this interval, for x less than minus 3. So minus infinity up to minus 3, and this interval from 3 to infinity. So 3 to infinity. So once you find where the second derivative is equal to 0, then you have possible inflection points. So you can check the concavity of a function by testing whether the second derivative is positive or negative. Now, if we go back to the possible inflection points, minus 3 and 3, we see that the concavity does, in fact, change sign. So the inflection points at x equal minus 3 and x is equal to 3, because it changes from concave down to concave up at minus 3, and then concave up to concave down at plus 3. Now, for a final answer in Hawks, you would actually indicate the x and y values. So you substitute minus 3 and 3 into the original function and see what values you get. So if I substitute x equal plus or minus 3 in here, well, if I plus or minus 3, I get 7 times 9 is 3 squared is 9, so 7 times 9 is 63, plus 21 is 84, and I take the cube root of 84. So that's my y value in both cases. And there you have it. So get the roots of a second derivative, based on what how you do that depends on what kind of function it is. Check if a second derivative changes sign from positive to negative or negative to positive. If one of those sign changes happen, that is an inflection point. And where the second derivative is positive is concave up, where it's negative is concave down.